All right, we take up the topic of oxidation reduction reactions today. And this refers to a process where electrons are moved or lost from one element and picked up by another element. So the term oxidation refers to the fact that electrons are lost by one of the elements in the reaction. And at the same time, the electrons have to be picked up by another element, and that's going to be electrons are gained, referred to as reduction. So I'm going to give you some examples for both oxidation and reduction, and just in terms of some, terminology, the oxidizing agent is the one that accepts the electrons. So the oxidizing agent accepts electrons, so that's going to be the one that undergoes reduction, so it becomes reduced during the process. And the reducing agent is the one that donates electrons and becomes oxidized in the process. So we connect the oxidation. The one that undergoes oxidation is the reducing agent. So this last term, oxidation number, I'm going to show you all about oxidation numbers in this video, but in terms of the definition, we really don't understand it yet because we haven't talked about electronegativity. But in any event, it's the charge an atom would have if both electrons in the bond were assigned to the more electronegative atom. That's something that this definition we can pick up again at the end of the semester if we want to. Let's not worry about it at all. Let's just look at the numbers of electrons that are moving in the various reactions. Okay, so here's a simple example. This is the reaction of sodium and chlorine to form sodium chloride. So you have two sodiums, two chlorines, and they react to form two sodium chlorides. So you're going to see on the next slide that there's some rules for how to assign oxidation numbers. And I'll show you that in just a second, but let's say, for example, that they're assigned already. So you put them above the element, 0 and +1 for sodium, -1 for chlorine. And the rules that you're going to see in just a minute is that if it's an element in its elemental form, so the elemental form is what state will the element be in if it's at standard conditions, the standard thermodynamic conditions, which is 1 atmosphere and 25 degrees C, so or 298 Kelvin. And the answer is sodium is going to be a solid, and it just occurs as an array of sodium atoms. Just sodium exists neutral in a neutral form by itself. Chlorine, on the other hand, if you find it at room temperature and so on, you'll see that it exists as a diatomic molecule. So what is the form? The standard form or the elemental form is Cl2 in this case, so that chlorine gets an oxidation number of 0. Sodium in its elemental form here is going to have an oxidation number of 0. Once it's in the ionic form, we will find that for some of the simple elements, by that I mean groups 1 and 2 and 13, so the representative elements, whatever charge it is that they assume when forming an ionic compound, that will be the oxidation number assignment. So it'll be +1 in the case of sodium. Each chloride has a -1. So you can see the change here. Oxidation of sodium, it's lost an electron, and so it's going to become positive. Reduction, it starts out neutral, 0, not neutral, that's the wrong word for it, just the oxidation number 0, and it picks up an electron that it took from sodium, and now it's going to be chloride, and so the oxidation number is -1. So we could do something like this. We could say, if you want to look at sodium, you could look at in products minus reactants, right? So you could say 2 times each sodium, which is +1 as the product, and then -2 times 0, the oxidation number of the reactant, and you got to get plus 2 electrons, and if it's positive, that means it's lost, right? So chlorine, start products minus reactants again, so you're going to take 2 times minus 1 for chloride here, and then for the reactant, it'll be 2 times 0, right? So this ends up being negative 2 electrons, and that's associated with the chlorine gaining an electron. So you find that the electrons lost by sodium, the number of them equals the number of electrons gained by chlorine. And that is the nature of the oxidation reduction reaction. All right, here are the rules, and these rules you want to, I would attach to a written exam, or you're going to have them in front of you for an online exam. So you'll have this information here. So the rules that I just told you about on the last page are the first two. The oxidation number of any element in its elemental form is 0. I use sodium as an example and chlorine as an example. In this case, it's magnesium. But, diatomic molecules, hydrogen and oxygen, the hydrogen will have 0, oxygen will have 0. In the case of P4 here, that's the elemental form of phosphorus, so it's going to have a 0 as well. So all of these will have 0. Any oxidation number of an ion equals the charge of the ion. So sodium in the plus state means it'll have an oxidation number plus 1. Okay, rules 3 and 4. The sum of the oxidation numbers in a neutral compound is 0. And the sum of the oxidation numbers of the atoms in a polyatomic ion is equal to the charge of the polyatomic ion. So I will show you all about that coming up. Then fluoride always is going to be -1. Group 1 elements are always going to be +1. Group 2 elements are going to be +2. Group 17 elements in a binary compound are going to be -1. So chloride here will be -1. And oxygen is normally -2. And then there's some exceptions. One of them is peroxide, the other one is superoxide. You could see, I'll come back to that, okay. And then hydrogen bonded to nonmetals is +1, and hydrogen bonded to metals is -1. So you don't see the hydride, this one is called sodium hydride. You don't see the hydride so much. The hydrogen is usually in the plus form for systems that we consider here. Actually, I'll explain the exceptions to oxygen here. Just make a little box. So if you have something like H2O, oxygen's behaving normally. Hydrogen's going to be +1 because it's bonded to a nonmetal. Oxygen is going to be, so you can think of it this way. You got 1 oxygen. It's like that crisscross rule again, right? -2. So 2 times +1 plus 1 times -2 is 0. So here you're using the rule that the sum of the oxidation numbers is neutral is 0 in a neutral compound. So the sum of all of this is equal to 0. And then if you have one of the exceptions, H2O2, then look at hydrogen. It's bonded to a nonmetal, so it's going to be +1. And the only way this is going to add to 0 is going to be if oxygen is -1. So you have 2 times +1 plus 2 times -1 equals 0. All right, and so you have this unusual situation that oxygen has an oxidation number of -1. Then the other one is a superoxide. So these are peroxides, right? And you have a superoxide. This is where oxygen is bonded to a metal. And in this case, sodium has to be +1. It's an ionic compound. You get one of those. And so oxygen has to be what? It's got to be 1 times +1 plus 2 times x is equal to 0 because it's neutral. So x is going to be equal to -1/2. So -1/2. And it's okay to have fractional oxidation numbers. So that is the superoxide. All right, so we're going to use these rules on the next slide, just some simple examples here. And what is the oxidation number of phosphorus and potassium phosphate? So in this example, you have things that are known. Write this over here. So K3PO4. Oxygen's behaving normally in this one, so it's going to be -2. Potassium is behaving normally. It's ionic, so it's going to be +1. And the thing about some of these elements is that they can have more than one oxidation number or state, and that is just depending on what it's bonded to. So in the case of this compound, potassium phosphate, you'll say 3 times +1 plus 1x plus 4 times -2. You're going to use the rule that says that sum of the oxidation numbers is 0 for a neutral compound. So you're going to go ahead and solve for that. Let's see, we got 3 -8 -5, put on the other side, so x will be equal to +5 for that one. All right, for permanganate, now rule, whatever that was, 4, I think, says that the sum of the oxidation numbers for the ionic, in this case the polyatomic ion, has to equal the charge, and the charge is -1 on the entire thing, okay, on the entire species. So let's write that out. MnO4 minus, and let's see, oxygen. So this, as I said, the sum has to equal the -1. Oxygen's behaving normally, so it's going to be -2. Manganese, we don't know, it just depends. All right, so then you're going to say, 1 times x plus 4 times -2. And this time we don't say 0, we say -1, right? So that's that right there. And then we can solve for that. We're going to put, we're going to add 8 to both sides. So this is x is going to be equal to +7 on that one. Okay. All right, the third one, it's permanganate again, but this time it's potassium permanganate, so it's going to be neutral. And we'll just keep working here. So KMnO4. So it's neutral. Oxygen's behaving normally. Potassium's as an ion is behaving normally. X you don't know. You got 1's here. So you're going to say 1 times +1 plus 1 times x plus 4 times -2 is 0. And you're going to get x is equal to +7 again. Manganese is still in the form of permanganate. And I guess, when you get better at this, you don't have to write out this as an equation. I would probably pick out the positives here, right, and the negatives here. So oxygen is going to be -8 total. And then potassium is +1, so it's going to be -7, and then it's got to have a +7 to make it equal to 0. So you figure it out yourself. There's different ways of thinking about that. So nitrate -1. So we're going to have the sum of the oxidation numbers here equal -1, and you've got 2 -2 for each oxygen, so -6 total. Plus what equals -1, and nitrogen's going to have to be +5. All right, if you don't like that, you can just say 1 times x plus 3 times -2 is equal to -1, and x will be equal to +5. All right, what else? So here are a list of reactions from this chapter in your book, and I've combined them to hopefully show you that all of these reactions end up with electrons being transferred. That's kind of the fundamental nature of oxidation reduction reactions. As opposed to the exchange reactions that we looked at in the big video for the chapter, and things like precipitates, those double exchange reactions. there's no change in oxidation number in those reactions. The motivating force for those is the formation of the precipitate, and the net ionic equation shows you that. But in this case, the motivation for the reaction is the changing places of the electrons. All right, so I showed you in detail information about sodium and chlorine combining to form sodium chloride. It is an oxidation reduction reaction, but you can also focus on the fact that it's a combination reaction. So you recognize the pattern here. A plus B forms C. So you have two things that combine to form one. That's a combination reaction. For the next one, water, this is a decomposition reaction, so you could say maybe C forms A plus B, something like that. And also, can't fit it there, so I'll put it underneath. Oxygen's -2, hydrogen's +1, hydrogen is 0, and oxygen is 0. So you can see clearly that this is an oxidation reduction reaction. So in other words, there's two ways to look at it. One is that it's just a simple decomposition. One thing goes to two, but the other thing is with the fundamental underlying process is the exchange of the electrons. All right, combustion is the one I wanted to show you in the next slide. It's kind of a fun, difficult example. And then also displacement, I showed you that already in the video, the big video for the chapter, and we'll look at that in a second. Okay, so bear with me on this single displacement. We look at the next one. I just want to show you this really cool example here. And I'm not going to ask you for anything as hard as this, but I just wanted to show you really how elegant nature is in this one. All right, so let's assign our oxidation numbers. We know that, let's start on the right here. Oxygen is -2, it's got to add to 0. You got 2 hydrogens, so each hydrogen is going to be +1. Oxygen is going to be -2 here, so you don't look at the coefficient 8, you just look at the molecule. So you got -4 for the negative part, and it's going to be +4 for the positive part, right? Okay, oxygen by itself is going to be 0, and then here's the hard one. So hydrogen is going to be +1 because it's bonded with a nonmetal, and then the question is, what is the carbon? Okay, so forget about the coefficient here, don't look at that. So you got this part here is +10, so this part here has to be -10. What will the oxidation number be for each carbon? Think about it a little bit. It's going to be equal to -10/4 or 5/2, right? So 4 carbons times -10/4 is -10, and that would be the carbon on the left there. All right, so then let's look at the change, which is the most interesting part here. So let's go to black. All right, so for carbon, I do products minus reactants. So let's start with the CO2 on the right-hand side. And you have 8 carbon atoms, each one is +4, okay? Then you're going to subtract the oxidation numbers for the reactant. So it's going to be products minus reactants. And this one is, you've got 8 carbons on the left, and each one is -10/4, right? So this is +32, and this is going to be +20. So this is going to be equal to +52 electrons. And because it's positive, that means electrons are being lost. And if you just go back and think about it for a second here, you got carbon with a -10/4 going to a positive. So if it goes positive, that's going to be oxidation or electrons lost. All right, and then the hydrogen is +1 all the way through, so don't even worry about that. There's no change there. That's not where the action is. But the oxygen is undergoing the change. And again, we're going to do products minus reactants. So in the CO2, you got 8 times -4. Or I guess you could say, let's actually change that here. So you have 16 oxygens right here. So you have 8 times 2 is 16. Each one is -2. So you have 16 times -2 for the oh, and then you got to add the oxygen for the water here. So you got 1 oxygen. Each one is -2, but you have 10 of them. So this is going to be 10 times -2. And for this one, you got -32 and -20. So that's going to equal -52 electrons gained. Through reduction, the oxygen gets reduced. And, oh wait, I forgot to subtract 0 from that. Let's see. This is the products here, and then you got to subtract 0. 13 times 0 right there, and you get the same answer. Oh, so that's pretty good. It's pretty interesting there. Yeah, I think it's actually remarkable. Here's a system that's got 52 electrons moving around for every 2 moles of butane, right? This is butane. That's what's in these lighters, right? Your cigarette lighters. Butane starts as a liquid, and then when it starts to burn, it's burning from the gas phase. 52 electrons for 2 moles. I had it before. All right, anyway. So that last reaction, I just wanted to show it to you again. And you look at the pattern for these reactions, and it's A is the metal in the solid state, and then you have BC is the molecule. It's a metal ionic compound, which is completely dissociated in the aqueous phase. And then the A bumps out the B, right? So you end up with B solid plus AC aqueous. So that's the situation if the reaction occurs. And you look at the this table for the activity series here, and if let's see, if if A is higher in the table than B, then the reaction will occur. So if A is higher in the table than B, the reaction will occur. So that means A prefers to be oxidized with respect to B. Close the door there, hold on. So iron is higher in the table. Where's iron? So the answer is yes, iron is higher. We're in luck. So zinc, where's zinc? Right there. And then magnesium is higher than zinc. So magnesium, we could just go ahead and do some predictions here. If you have iron plus iron solid plus copper 2 chloride, the question is, can you make copper solid plus iron 2 chloride? That's the question. So you want to look at the activity series, and if iron is higher than copper in the table, then the reaction will occur. So go back, table then copper. So the reaction will occur. And I'm repeating this because I wanted to show you the oxidation number part of this process. So iron's going to be 0, chloride's going to be -1, copper's going to be +2. And then copper goes to 0, chloride stays the same, and iron becomes +2. All right, so is it oxidation reduction? You've got iron 0 going to iron +2, so that's loss of electrons. And then you have copper 2, you have copper 2 going to copper 0, so that one corresponds to a gain of 2 electrons. And yeah, you can put the number 2 in there. 2 electrons and 2 electrons. All right, so then in the case of zinc and magnesium, look in the table. So the question is, and so this reaction, the first reaction will occur. Let's look at this one now. So it'll be magnesium solid if it reacts plus zinc chloride aqueous. And the question is zinc higher than magnesium in the table? If so, it's higher than zinc, and therefore this reaction will not occur. Alrighty then, this is the end of this section then on oxidation reduction reactions.